Hello again, and welcome to another installment of Captain Hook's Problem Solving in Physics. Today we're going to be looking at a 5-step problem dealing with traveling to the moon and traveling to Alpha Centauri and similar things. Again, problems in front of you. You can see this at the very bottom of this page as well. We're going to sort of go one part at a time and talk about how we're going to think our way through and try to figure out what the answer for each part is. I'll start with part 1. It says NASA's launching a rocket into space from Earth. This particular rocket burns its fuel for 5 minutes only and then turns off its engines. After that 5 minutes, the rocket keeps floating along through space at a speed of 10 kilometers per second, and it wants to know what the rocket's average acceleration is during these first 5 minutes. So, first thing I always do when it comes to solving problems like this, if I can, is I'm going to draw a picture just so I can see what's going on. Picture doesn't have to be super detailed, but just basic idea. So I'm going to start with our Earth. And over here we have a moon, and we have a rocket that's going between the two. So my rocket is going to be a square for the moment because it's easy to draw. And we know that the rocket starts not moving, so its initial velocity is 0 meters per second. And it's going to accelerate for 5 minutes to a velocity, which is going to be its final velocity, of 10 kilometers per second. And then it's going to keep at that velocity all the way till it gets to the moon. So this problem, the first part wants to know what its average acceleration is during these first 5 minutes. Well, before we can do that, we don't really deal with minutes and we don't like kilometers. We always like everything in meters per second. So we can convert those. To go from 5 minutes to seconds, we just know that there's 60 in 1 minute. There are 60 seconds. So if we multiply that, we get 300 seconds. So that is our actual initial, that is our time for this first part. And we also know, well, that 10 kilometers per second, that there, in 1 kilometer, there is 1,000 meters. So we're going to cancel those out, multiply across, and we're going to get 10,000 meters per second. But again, we try to use scientific notation if we can. Well, we move the decimal place 1, 2, 3, 4 spots over, get 1 times 10 to the 4th in meters per second. So that's sort of our initial or our final velocity, our time, and our initial velocity is 0. So if we come down here, we're going to make a little chart real quick. We know final velocity is 1 times 10 to the 4th in meters per second. Our initial velocity is 0 meters per second because it starts out not moving. And we know the time it takes to go from here to here is 300 seconds. So now we have to look at our average acceleration equation, which is simply, the acceleration is simply the change in velocities over the change in times. So our final velocity minus our initial velocity over our final time minus our initial time. And that's going to give us, well, if we plug in the numbers, our final velocity, we already said was 1 times 10 to the 4th in meters per second minus 0 meters per second. Over, well, our final time was 300 seconds minus 0 seconds. So if we put all that together, well, that minus 1 times 10 to the 4th minus 0 is just 1 times 10 to the 4th in meters per second over 300 minus 0, which again is 300 seconds. So if we will do 1 times 10 to the 4th divided by 300, that's going to give us about 33. And now we do our units. Meters per second divided by seconds gives us meters per second squared. So that is our average acceleration for getting from 0 meters per second all the way up to 10 kilometers per second in 5 minutes. It's 33 meters per second squared. So that's our first part. We look at our second part. It wants to know how far the rocket traveled during that first 5 minutes. So in that first 300 seconds, how far did it go? Okay, so again, we've got our same picture, not much has changed. We're just trying to find the displacement now. We're trying to find the distance that it traveled till it got to 10 kilometers per second. Okay? Well, this is when we got to look at our kinematic equations. So we got our equations here. Well, we know what we know and what we don't know. Okay? So let's write down what we know again. So we know that our initial velocity is 0. Our final velocity was 1 times 10 to the 4th meters per second. Our time was 300 seconds. And now we know our acceleration was about 33 meters per second squared. So that's what we know. And what are we trying to solve for? What are we trying to find? Well, we're trying to find how far it went. We're trying to find its displacement. So this is what we don't know, okay? So if we look at our original kinematic equations, well, there's gonna be one that, so final, well, it's gotta have acceleration, it's gotta have displacement in it. So let's look at the ones that have displacement, because that's what we're looking for. So it's one of these two. We actually could use either one, but I'm gonna go with the simpler one. We have our displacements, our initial velocity times time, because we already know that's 0, plus 1/2 times the acceleration times time squared. So we're gonna write that back down again. So we have distance, or initial velocity times time, plus 1/2 of the acceleration times time squared. Okay. Right, now, we know that the initial velocity was 0, so this is gonna go to 0, because 0 times anything cancels out. So our final equation is going to look like displacement equals 1/2 of the acceleration times time squared. Right? So this is sort of, we got the variable we're looking for by itself, so sort of a time for plug and chug. So we're going to plug it in. 1/2 of the acceleration, which was 33 meters per second squared, times the time, which is 300 seconds, that unit squared. And if we plug that into a calculator, our displacement comes 1.5 times 10 to the 6th meters. Now, obviously you have second squared, canceling out with second squared, that's why we have our meters left. So checking the units in the end, using the units on the way is always a good way to check to make sure your answer makes sense. But there is our answer for part 2. All right, so let's look at the third part. Third part now says the moon is about 3.8 times 10 to the 5th kilometers from Earth. At its final speed, so that's 10 kilometers per second, how long will it take the rocket to reach the moon? Now at this point, we're going to assume that it's going at its final speed, it's 10 kilometers per second the entire way. So again, we're going to start out with a little picture here. Let me get this thing out of the way. We already know that it's moving, its velocity is 10 kilometers per second. Again, it's moving at that speed all the way to the moon, and that total distance was 3.8 times 10 to the 5th kilometers. So again, we're going to neglect the first 5 minutes, because comparing that first 5 minutes to the actual full distance to the moon, it's not that much, so it's not going to change the problem that much. So we're just going to use the simple velocity equals distance over time equation. Velocity equals distance over time. But we're looking for time, because we know our velocity and we know our distance, or displacement. So we just need to rearrange it, do a little bit of algebra. We're going to sort of cross multiply. So we're going to get time equals distance over velocity. So again, we've got the variable we're looking for by itself. So again, we can plug it in. In this case, both of them are already kilometers. So it doesn't matter if we change units, because that's going to cancel out later. So if we do this, we're going to do time equals our displacement, which is 3.8 times 10 to the 5th kilometers, divided by 10 kilometers every second. When we do our division, our units are going to cancel out. So kilometers is going to cancel with kilometers. This is going to go to the top. So our final answer is going to be in seconds. So that should just end up to being 3.8 times 10 to the 4 seconds. But again, that doesn't really mean a whole lot to me. I don't know if it means much to you, but we'll put it into hours just to make it a little second, or a little simpler to understand. Again, this is a perfectly correct answer. But again, if you want to sort of see what it means, we'll convert from seconds to hours. And if you don't know, there's 3,600 seconds in 1 hour. So all we have to do is take this 3.8 times 10 to the 4th seconds, and we're going to multiply that by 1 hour over 3,600 seconds. Again, because these are the same numbers, like multiplying by 1, our seconds are going to cancel out, and we're going to get about, again, I'm rounding after we do it, about 11 hours. Now that seems pretty quick. That is actually a few times faster than what the current rockets or anything we know right now that can do. Right now it probably takes about couple days, maybe a few days for, to get to the moon with what we have, with technology we have, but still, that's pretty quick. So the moon's really not that far away. Okay? All right, so that's that part. Part 4, let me bring this back over here. Part 4 says the star nearest to us is called Alpha Centauri. It's about 4.1 times 10 to the 13th kilometers away. So if you compare that, that is a big difference from the moon. Okay? The question asks, could this rocket get a man to Alpha Centauri before he dies of old age? This would be a neat thing to see. Again, if we're going at 10 kilometers per second, we're going to set up the problem the same way we did last time. So again, we know this time we have somebody at Earth, and they're going at 10 kilometers per second all the way to Alpha Centauri. Okay? All the way to Alpha Centauri. And we know that that distance is 4.1 times 10 to the 13th kilometers. And we just want to know how long is it going to take to get there. So this is the same equation we used last time. I'm going to go ahead and skip to the reordered version, where time is just distance or displacement over velocity. So we set it up, 4.1 times 10 to the 13th kilometers. We divide that by our speed of 10 kilometers per second. Same idea as we set up last time. Again, our units are going to cancel out, and we're going to be left with seconds. So if we put that into a calculator, 4.1 times 10 to the 13th divided by 10, we're going to get 4.1 times 10 to the 12th seconds, which again, we want to convert to years. So 4.1 times 10 to the 12th seconds times 1 hour over 3,600 seconds. So the seconds are going to cancel out. And then we have to do hours to days. Well, we know that there's 1 day and 24 hours. And then years, we'll say 365, because it's about average, 365. 1 year is 365 days. So again, if we go through and cancel out the units, seconds cancel with seconds, hours cancel with hours, days cancel with days, and we're left with years. So we plug all that into a calculator, you multiply across the top, divided by what's on the bottom. We're going to get that is about 1.3 times 10 to the 5 years. So if we put that into regular numbers, that is about 130,000 years. So with what we have right now, I don't think anybody's going to survive that. So it seems like a problem that if we ever want to travel to another star system, we're going to have to figure something else out. All right, we've got one more part to go. All right, now we have original rocket going back to the moon again. We gets partway there, and the pilot suddenly notices he forgot his camera. He radios a second rocket crew on Earth and tells them to bring his camera and meet him on the moon. Seems silly to me, because that's a lot of money just to bring a camera, but it is what it is. So he wants them to meet them there before he lands. So unfortunately, the second rocket can only accelerate 3 meters per second squared. So it can't accelerate as fast, but it wants to know, can the second rocket make it to the moon before the first one lands? So the key to this problem is we already know how much time it takes the first one to land. If we look back at what we had before, we'll get to that in a minute. But the key to this one is that rocket can accelerate the entire time. So we're going to deal with rocket 2, going from Earth, drawing our picture again. Rocket 2 is a circle, because sure, why not? Because it has an acceleration of 3 meters per second squared, and it needs to get to the moon, which again is the same distance as it was before. So we're going to go with So we're going to, we solved the problem for distance earlier. We'll get back to that in a second. But again, we use the same equation that we used before. Distance equals 1/2 AT squared. Again, we're ignoring the first initial velocity because again, for the second rocket, it's also 0. But we're going to assume in this case that he can accelerate the entire way. He doesn't just go for 5 minutes, he can accelerate the entire time. We want to know how long it's going to take to him if he continually accelerates. So again, we got to reorganize this to solve for time. So first thing I'm going to do is multiply both sides by 2. cancel those out. So we got 2 times d equals at squared. We'll divide both sides by a. And again, we're trying to get t by itself. So those cancel out. 2d over a equals t squared. And then we just have to take the square root of both sides. Okay. So when we do that, we're going to get t, and just going to reorganize it. T equals square root of 2 times the distance over the acceleration. Okay. So if we plug in our numbers, we have square root of 2 times 3.8 times 10 to the 5th kilometers. And again, we'll just do our little conversion in here. Let's say the 1,000 meters over 1 kilometer. So that's 2 times our distance divided by our acceleration, which our acceleration is 3 meters per second squared. Again, kilometers are going to cancel out there. We're left with meters on the top. So if we plug all this in into our neat calculator, we're going to get 1.6 times 10 to the 4th seconds is the trip it will take, which if we convert that into hours, so we multiply by 1 hour over 3,600 seconds, we're going to get that it will take about 4.4 hours. That's with continual acceleration. So he can make it in time, but he's going to use a lot of fuel. And that is the end of the problem for today.